All right. Good afternoon, everyone. I'm super excited today to have Daniel Rosenwasser from Microsoft here to talk to us about TypeScript and kind of the design decisions that went into TypeScript and some of the lessons learned over the last few years of them developing TypeScript. Daniel is a PM on the TypeScript team, has been for the last 3 years, and has led some of the efforts there on developing the new type system, rewriting the compiler, and also the language service, which is this kind of interface between IDEs and programming languages, so that you don't have to develop auto-completion and error detection for every combination of those two, but that you have a kind of common interface between those two. And yeah, so super excited to have Daniel here, and looking forward to an exciting talk. Thank you.
Like Dominic said, hi everyone, my name is Daniel Rosenwasser. I'm a program manager on the team. For about 3 years I've been doing that, and 2 years prior I was an engineer on the same team. And so by just show of hands, who here has used TypeScript before? Wow, okay, that's pretty cool. Who here is not that familiar with it in general? Okay, great. So just to start things off, I'm going to tell you a little bit about what TypeScript is. So a couple of years ago, back at Microsoft, we found ourselves needing to build more and more applications for the web. So as an example, we needed to start building Word online and Excel online, et cetera. But what we found was that our engineers at Microsoft were a little bit averse to using JavaScript for their applications. They instead chose, certain teams actually chose to develop a compiler for C# down to JavaScript as just an example of what some of the things that we were doing. And this is not like a very unheard of idea at the time, but you also have companies like Google doing something similar where they took Java code and compiled it into JavaScript using a tool called GWT. And at some point we had to ask ourselves, is this something that we could see engineers on the outside of Microsoft doing? And the answer was no, probably not. We didn't think that we had neither the community backing or the inertia, nor just we didn't think we could even convince JavaScript users to do something like using C# to build web applications, because it's just not what they were doing themselves. And so what we instead asked was, what's missing from JavaScript that has all these engineers flying to try to use something like C# to develop their applications? And so if you think back to the context of like when this stuff was coming together, it was around 2010. And at the time, you're missing modern constructs in JavaScript, right? At the time, for the record, JavaScript's formerly called ECMAScript. That's the standards name for JavaScript. And at the time, we're on this version of ECMAScript called ECMAScript 5. That's the state of the art. And that's pretty nice to have if you have the right browser engine. But it doesn't have things like modules. So you end up having to basically wrap your entire your files in these function bodies just to emulate scope so that you don't have globals colliding with each other. You're missing things like classes. So you end up having to do prototype chain mucking around, and you have to really understand how prototypes work in JavaScript to do anything that's OO related. You have a bunch of issues around capturing the value of this if you're familiar with JavaScript. But you're missing modern constructs. And while this is a point-in-time problem, right, there's a standards committee called TC39 that's eventually going to introduce these new features. They're just not present. But the other thing that we realized was missing was, well, JavaScript has a lot of these sort of funny semantics around coercions and automatically comparing strings and numbers a certain way, and multiplying strings is allowed, even though it's like kind of nonsensical in a lot of contexts. And issues with like undefined is not a function. If you've ever worked with JavaScript, this is just something that you always see in your console when something goes wrong. And so we realized a lot of these things can be caught by a type checker, right? Like you don't need to wait to run your code in the browser if you have a static type checker to see whether or not you've misspelled a property or something really basic like that. And the other thing that we learned for years prior at Microsoft was that once you have a good type system, you can build really good tooling. So once you have a system that knows whether or not you can actually access a property on an object, you can also build a tool that can predict what properties you might want to autocomplete with in your editor. You can actually find the references to certain declarations and find where people are using certain things, find where a function is called. And so we said, instead of trying to push people to this existing language, because it is extremely hard to push people to an existing language when there's a community behind an existing one, what if we just say, we're going to make this new thing called TypeScript. And all it is JavaScript with all of the new constructs, but with a type checker. And once you have these things in place, you can actually build good tooling around everything here. And so, fast forward to today, it took us a little bit of time to understand what we were, but our project kind of tenets are thus, right? We are open source and we're open development. To actually build a language in this day and age and have it succeed, typically you really need to have it be open source, and you need to do open source a specific right way, in a sense, right? You have to actually do it so that the community is behind it, so that you have transparency and things like that. And that gains you trust, but it also is just sort of the de facto anyway. And so if you're not there, you're just not going to gain the right crowd behind you. The other thing that we learn is, at first we're thinking, well, it's not just JavaScript with types, but it's also maybe some other stuff that can help you that we think might eventually land in JavaScript. And eventually what we decide on is we're going to specifically only track what ECMAScript does in terms of new features. We're not going to add anything that compiles down to JavaScript that is not part of JavaScript. But instead, what we'll do is we'll add a type system with type syntax that can be fully erased. And that's kind of our goal now. We fully invest in adding type features that can be stripped away, and we're purely interested in the type checking process now. And with that allows us to give you really good editors like Visual Studio and Visual Studio Code. Not that you're limited to those either. So because everything's open source and everything is cross-platform, you can just use this in an editor. And we're really invested in the community. So a big part of this is to actually make a type system that anybody can use, right? So nowadays, you have a lot of JavaScript users who are not familiar with any other language. They've never used a type system before. And so this needs to be approachable. So that's where we are now, right? This is how we got to our tenets. But at the time, we weren't quite there. And when we started out, I want to just take a look at this quote. Who here is familiar with the book Types in Programming Languages? Okay, so if you've taken a PL theory class, then you might be familiar with this. This is a red brick book by Benjamin Pierce, and it has a really great section here. And I came across this a couple of years back, and it says, retrofitting a type system into a language not designed for type checking in mind can be tricky. Ideally, language design should go hand in hand with type system design. And off the bat, from the textbook definition of ideal language design, we're already doing the wrong thing, right? We've already sort of screwed up. But you really can't let that stop you, right? We have what I think is a good goal in mind. And so we come out with TypeScript, which is modern JavaScript with types. And for the record, I should say, if anyone has questions during this talk, you should feel free to ask them in the middle. If you need something to be clarified, I welcome that. But anyway, so we have Dominic. You have a question?
About this modern JavaScript, can you say a little bit about what that means in terms of compiling down to like previous versions?
Sure. So Dominic asked what exactly it means to have modern JavaScript and types, and that is a good point. I should clarify that. So you typically need to be able to use the most modern version of JavaScript. However, you're often dealing with some older browsers, and sometimes you don't have the internet to show something off. No worries there. Here, let me give you an idea of what I'm talking about. Can everyone see this? Let me zoom in here. Okay. Better? Okay, great. If at any point you can't see what I'm doing, please let me know. So TypeScript comes with a compiler. And the idea here is you take a .ts file, which is a TypeScript file, and you compile that down. And what you're left with is what we hope is clean, readable JavaScript. So if you take a look here, everything looks fairly similar to what we originally gave, just to put them side by side. You have an interface in the original source code, which is a type declaration, but it's gone in the right-hand side, right? Types are completely stripped out. Similarly, we have type annotations as well. And type annotations are also stripped out. But then the modern JavaScript thing comes in right around here. So in newer versions of JavaScript, you have a thing called a let declaration. It's like a variable declaration, but it has better scoping behavior in general. And so what we're able to do is we're able to what we call down-level this code so that you can run it in an older browser like IE 8 even, or even farther back than that. Nowadays, we're fortunate enough to have these what we call evergreen browsers. And so they're always just updating constantly. You get a new update basically every 6 weeks or something like that. And so if you're targeting a newer browser, you don't care as much about this. But if you need to go back to IE 6 or something like that, which I'm not sure if everyone in this room has used IE 6. I'm just thinking about that now. Yeah, won't think about that. Yeah, that's a blessed life, exactly. But it's definitely a concern back then, more so than it is now. But it is still a constraint for a lot of people that you need to target older versions. So at this point, we come out with something that can take modern JavaScript and down-level it to older runtimes, something that you can run in older browsers. And it adds types. And so, of course, everyone loves this off the bat, right? We're going to get everybody. Not so much, right? You know, we came out with something that was attractive for some users. You have a question back there?
Yeah, so when you're converting to older versions of JavaScript, are you using type information to help with that? Or are they like completely orthogonal?
The question was, do we use type information of JavaScript? We don't. We try to avoid what we call type-driven emit in any possible capacity. The idea is we're supposed to try to be as you should be able to just erase the types away completely. And that way you don't get this feeling of like lock-in, but also because our type system is not actually fully sound, you don't have to, you're not basically emitting wrong code all the time. That's a big part of it. We do have some stuff that requires resolving across files, but we don't do anything like that anymore. So any new construct in TypeScript doesn't do this. So we released TypeScript, but it doesn't quite, some people are already alienated from this, right? They haven't even tried it yet, but they already got this, negative connotation with it. Because what they kind of think is, oh no, types, like this is terrible, right? I've been using JavaScript and you're telling me that I'm not writing good code because I don't have a type system. And some people will say, I have used type systems and they look like this and I don't like it. And so this example is specifically Java code. And it's not that Java is necessarily a bad language, but it gets a bad rap for things like verbosity. And so you end up with these like statements like array list of dog named dogs is a new array list of dogs. And it feels like a Markov chain has sort of gone off the rails in some capacity. And you're like, all right, yeah, And so we, even when we first come out with TypeScript, we know that this is going to be like one of the big concerns that users have. And so we have this actual quote from Types and Programming Languages again, and I'll paraphrase. The question of whether or not, or the idea that type should be a part of the programming language is actually a separate idea from whether or not you have to write down the types when you're writing your program. A well-designed language should not require a lot of type information to manually be written down in your programs. And so this refers to type inference, typically, right? The ability for your compiler or type checker to actually take a program, figure out the types without you having to say what they are specifically. And so this gives us a couple of goals in mind, this is just where we need to go to actually build a language that people will like. First, this language needs to support both unannotated and untyped code. Notice that I've drawn a distinction between unannotated and untyped. So there's this concept of untyped code in TypeScript, which we'll go into in just a moment. But there's also, this brings us to point 2, which is you need to actually bring some value in the presence of unannotated code. You need to be able to actually infer some types when you're building a program. But there's a constraint here, which is you can't just infer from everywhere within the program. And so we'll go into each of these goals in just a minute. So taking a look at gradual, so this brings us to a design of what's called gradual typing and using type inference. So let's take a look at this cost function. Let me pick up the water I just dropped. Let's take a look at this cost function. There's nothing wrong with this function, but I want us to, let's start off with the question of what is the type of cost? Well, in order to find out the type of cost, you need to know the type of items. And in this context, the type of items is what's called any. And even though we didn't actually write it out, TypeScript has inferred the type any because it hasn't been able to infer a better type. And so what is any? Any is the untyped type. It allows you to do anything you want with it. You can dot off of it, you can call it, you can add it, you can multiply it, you can throw it into a blender. You're allowed to do anything you want with this thing, right? And so even though we're not annotating it, it's implicitly any. So, that's kind of a bummer because the point of using TypeScript is to actually get a type system to help you correct your errors. Now, any is effectively opting out of type checking, right? It's actually kind of falling back to JavaScript. And that was kind of one of the sells of TypeScript is that, okay, even if the inference doesn't work out that well, you're always just falling back to JavaScript, and that's your worst case scenario. And that was what you had before you had TypeScript anyway. But we can do better here. So for example, total. Total is trivially, you can infer the type number because total is initialized with the value 0. When you have that, you can effectively look through the flow of the program and then figure out that you have a return type annotation, or sorry, a return expression. You see that total is returned, and so the type system actually infers number. And so while there's caveats here, right? Like some of this is making assumptions because any is already unsound. But by and large, we're able to deliver some value anyway, right? So we do a limited form of inference that is sort of statement local. You have a question?
Well, given that we can reassign anything with any value at any time, I assume you can cope with that and basically things revert to India at that point? Or if somebody made number equal hello mom in the middle of the function somewhere.
Right. So the question was, how do we deal with conflicting assignments that may occur later on? So in the presence of an initializer, we typically assume that you're not going to reassign with a different type entirely later on. Now, if you're doing some loosey-goosey sort of code, or if you're basically starting out with a very derived type and then you later on assign a less derived type, then that's something that would require you to add a manual type annotation, right? You manually have to type that out. Generally speaking, we don't find that those are that common in practice. But in stricter type checking modes, if you have no initializer and no annotation, we actually use control flow analysis to analyze your program and figure out how those declarations will flow and whatnot. And those are very flexible. And we can try to take a look at those in just a bit. So we're able to do this inference that's sort of limited to the statement level. We're able to actually infer from callbacks and whatnot. And so that's actually works for maybe like 90% of the cases, right? You know that an array of numbers takes a callback that takes numbers. And so you immediately get completions and things like that working in your editor. And that works out pretty nicely. People often ask us, type checking is a solved problem, right? I use standard ML, or I use Haskell, or I use OCaml, or F#, or whatever. Why don't you just do that? Why don't you just do what they did? There's a couple of problems with it, right? First of all, It's not the most efficient way to type check. I should rephrase that. We have constraints within the editor. You need to be able to take any expression. You need to be able to hover over any identifier in your editor, and you need to be able to answer what the type is there and display it back properly within 250 milliseconds. Actually, even less than that. But 250 milliseconds is kind of like the, oh no, something's really wrong with my editor, baseline that we have. And so you need to be able to answer these things quickly. And so if someone starts typing something and that requires a full type check of your program, that's potentially an unacceptable delay because that will likely take up to a second in a lot of cases. So we can't do this like global sort of inference that a lot of people have in mind, especially since we have things like implicit subtyping and things like that, if you're familiar with those problems. So that's one issue. We have an efficiency constraint. We also have a how would you phrase this? A user-friendliness constraint. So if someone has a well-typed program and they call a function incorrectly, and that changes the types throughout the program in a way that is non-local, that's extremely confusing, right? One of the problems with these type checkers that use non-local inference is that they typically take a look at the whole world, and anything in the whole world can be affected through what's effectively unification. So we call this like spooky action at a distance inference, right? You don't want to give the user the sense that like they can't tell what's happening from the inference process. We try to be fairly predictable about what we do. Any questions about any of that? Inference and gradual typing at all? OK, sweet. The other novel thing that TypeScript has when it first starts out is structural typing. So you have basic types like number and string and Boolean, right? But in this example, we have a point parameter. Point has an x and it has a y, and presumably those both have to be strings, right, or numbers. But the idea is that point has two properties on it, named x and y. And the thing that you notice in JavaScript is you actually don't care how the thing was declared as long as it actually has those x and y properties. And this is typically called duck typing, because if it walks like a duck and it talks like a duck, then it must be a duck, right? So if it has an x property and it has a y property, then it must be OK for this function. And that's the philosophy in JavaScript. So as an example, like you can specifically call this origin distance function with an object literal in JavaScript. You can create a class, and then you can instantiate the class. It doesn't matter. JavaScript's OK with it. So the way that we model this in TypeScript is through something called structural typing. So rather than having to rely on the way things were declared or where they were declared, the idea is you effectively just write this interface, this type called hasXY. HasXY just says that it has an x, which is of type number, and a y, which is of type number. And anything that is compatible, anything that has those right properties, is compatible with the hasXY. So in this example, coordinate doesn't implement hasXY, if you're familiar with that concept in Java or C# or whatever. But it's implicitly compatible because each of the members is compatible as well. And so in this example, we're using an instantiation of a class. We can also use an object literal. And the key idea here is that that each of these declarations of P up here are completely equivalent, right? You're able to dot off of them and get the same members, and that's OK. And you're able to assign them all to each other. We have a question back there.
Yeah. So earlier you showed type inference, and that method body used a field, but you showed it inferring the argument as any rather than as having that field.
Are you talking about when I had the editor open earlier, or are you talking about
total plus equals points for item and items?
Oh, so the question was, we had some type inference, and things just sort of worked. So
Items is a collection of some sort. Why don't you infer that it is a collection? or a collection of things that are priceable.
I see. So why don't we? The question is, why don't we infer that? Why don't we infer that items is a collection because we're able to iterate on it, for example, or that we're able to dot into each of the individual members and take a look into price. So that is another example of use site inference. And we could potentially do that in a limited scope, but it has some of those same issues of non-locality with the inference process, and it can potentially be a little bit expensive. We've experimented a little bit with this, and sometimes the types end up being somewhat nonsensical as well. And so that cost, as well as the ability to display types in a reasonable manner, and in addition to having that predictable behavior, is something that leads us to not do this. So as an example, items is inferred at its declaration site. It doesn't look at use sites to determine what it needs to be.
So essentially your take is use site inference feels too whole programmy, and you don't want to do whole program inference.
I think that we are somewhat, so the question is, use site inference might feel a little too whole programmy. It's not exactly whole programmy, but it has some of the same problems of spooky action at a distance. We're not experimented with it a couple of times as well, with naive implementations as well. And I'll never say never, right? We're willing to consider something if it has desirable properties, but we're sort of feeling it out, and we feel like we've got a reasonable balance. Other thing is, we do some of that use site inference in the editor, and so we do have some quick fixes and things like that to say, hey, notice that we might be able to infer your. Would you like to manually annotate those things? And so that means that that's kind of like a form of caching, right? You do it once in the editor, and then you never have to do it again, and so that becomes cheap.
Is that then reflected in the source code too?
Yeah, it stays in the source code. We had another question.
I had the same question as Mike.
Okay, gotcha. So the question was, why don't we use sites for inference? Which is totally valid. I think it's an important one to ask, right?
Sorry, but I have one more question about the same example, which is why. So I understand correctly here. You infer that the return type of the function is number, but if one of the items dot price is like a string or whatever, then that is one way to break your type system, correct?
Yeah.
Okay,
So
cool.
in the original example, because you ended up with items of type any, yeah, you could have had an item with a price of string. But the thing is, any is already the escape hatch. It's the untyped type, so you can break the type system like that, and that's. Yeah, we could default to any, but again, that comes down to one of the constraints, which is you have to be somewhat useful in the face of untyped code, right, and unannotated code. And if you just basically poisoned everything that had the type any, you would likely end up with something that is not useful. You just end up with any's everywhere because that can poison the well. And so the idea is we take a kind of altruistic view, like, yeah, it's a number, but as soon as you're probably not going to try to work with strings in there. And who knows? But like you probably you intended for that to be a number, right? And then once you actually add the types in, we can yell at you that you did the wrong thing. It's a trade-off. You're going to have a really hard time. Again, this is probably one of the goals I should have mentioned. We don't specifically aim for soundness in our type system. We're aiming for good behavior, and we strive for soundness, but it's not like a deal breaker if we can't get it effectively. That's the idea. Yeah. What another question?
Since you guys some form of gradual typing, can you guys like add some one-time task to make everything, like add some one-time check to make sure everything like is?
So the question was, can we inject runtime type checks to ensure that you have some sort of soundness, like to error at runtime? Yeah. So that there's the question is, can we inject runtime type information based on type annotations? That goes against effectively two things, right? One is not emitting type directed emit at all. because that's just something that we try not to do. But the other, actually, there's three. The other is, how do you validate that something has the right types in a lot of cases? Everyone has a different idea of schema validation in JavaScript, and so you can do the full structural check. Some people just say, oh, you should just do an instance of check in JavaScript for when you have a class. And no one really has a definite answer of that. And the third thing is that it typically is pretty slow. We've worked with a couple of researchers who have come to us and said, like, hey, we worked on a project which can ensure that you have sound code at runtime, and it basically errors out if you're ever about to do something that's invalid. And sometimes the results have been pretty decent, but typically there's a lot of overhead in doing each of those runtime type checks. And actually, Google had something similar with, I think, either their SoundScript or SafeScript project, or something named to that effect. But the idea, there was a SoundScript, SaneScript, SafeScript, and something else. And I don't remember what each of them was. But the idea was, none of this works in a compatible way with other JavaScript code. So like you can't run it in real world scenarios. And it's also really slow because you have to inject those checks to ensure that you're actually running valid stuff. We have one more question?
Yep. Can you clarify what you mean when you say it may not necessarily be sound? Do you mean the fact that it has any, or do you mean there are features that are inherently unsound? Because I know that there used to be like, I don't know, contravariant and covariant issue, and then you, at some point you fix it,
Right.
I think. But are there still like any other issues that just like that?
So the question was like, what do I mean by sound in general? Is that effectively the question? Yeah. So soundness, for those of you who don't know, is the principle that like a type system should strive to actually stop any programs that would get stuck or would not be acceptable in some definition of that system. Question is, what do you mean by stuck? What do you mean by like in a bad state, right? There's really a trade-off there where you have to kind of draw a line, and there's also the fact that soundness is, this means that soundness is effectively a not dial. It's like a spectrum effectively, right? Like this is more sound than something else. So you can sort of tighten the knobs and try to stop what would not work in the future. You can stop bad code from running in the future, right? So you can become more sound for some like informal definition of that. But you are sacrificing completeness, which is the fact that you allow well-behaving programs to run in the first place as well. And so there's that trade-off. So you have to basically determine what sorts of things are we going to tighten to like stop bad programs from occurring, and what sorts of things, what are we willing to stop permitting to get more soundness? We're not fully sound. We do add checks under like strictness flags, so we'll have like strict function types for better contravariance checks on functions. We still have mutable properties that are compared covariantly, and that is an unsound thing in basically any programming language that I know of. But you have to determine what your measure of soundness is, and we know that there probably is an arbitrary one, and we're not trying to hit it necessarily. But we are willing to add strictness checks if we feel like they're going to protect people from writing bad code. I think I should probably start moving on, unless, okay, great. Generic types. So structural types I just mentioned. That's kind of neat. Go also has structural types, but they don't have generics yet. Yes. We beat them, right? No, I'm kidding. Feature creep, someone said. Yeah. So for those of you who are not familiar, generics are the idea that you can parameterize types. And so as an example here, I have this foo interface. Foo is parameterized by t. And the idea is I can actually just say I have a foo of number, and that just replaces t throughout the declaration with number. And so a num foo is a foo where the property prop has the type number, right? Seems sensible, right? That's pretty easy. But this also gives us a couple of problems, right? So we have, let's say 2 interfaces, bar and foo, and each of them declare a property named prop, but bar is declared as a bar, bar's property is declared as a bar of t, and foo's property is declared as a foo of t. Okay. But TypeScript has a structural type system. And so how do you know whether or not a foo of number is assignable to a bar of number? Well, you start off with the question, is foo of number assignable to a bar of number? Well, in order to do that, I need to know whether or not a foo of number is assignable to a bar of number, because we have to go into the prop property and see whether those types are compatible. Well, okay, what is the prop property? Are the prop properties of those 2 things compatible as well? So you expand out and you say, is a foo of number assignable to a bar of number? And so, well, we have to answer whether or not, and it keeps going and right, like it goes a little bit crazy. And I have a hint, like you don't learn anything new by going another level deeper at any given point, right? And so these infinitely expanding types were a big problem for us until we just said, screw it, like you cut off at the 5th level, right? Five's a good number, right? Right, it works for C++ templates, right? Like there's a recursion limit at some point, and so they, this graphic of like the world sits on a turtle and what's beneath the turtle, another turtle, and you keep going. We call this the turtle cutoff, right? Like we keep an instantiation stack to try to determine this, and we say, all right, if we've seen 5 instantiations with the same originating symbol, so we've seen foo 5 times in this stack, then we're not going to learn anything new during the relation process. And so we say maybe the types are related, and then we continue going and seeing whether or not the other structure of the type is related. And that actually saves us from like the runaway recursion problem where we either blow the stack or run out of memory or a whole slew of problems. And I think like in the 4 years that we've implemented this like cutoff, one person came to us and said like, hey, this operates a little funky, I just noticed. And we're like, I mean, the underlying runtime typically protects you from this anyway. So at this point, we have a type system that is generic, it's structural, it uses gradual types, it does some type inference. It introduces modern constructs like classes, so you can do some OO programming and whatnot. But we realize that we're not necessarily modeling code the way that a lot of JavaScript users use. So what I mean by this is typically called the expression problem, where the way that we were getting polymorphism for a lot of users was through virtual dispatch on classes, right? This is a very OO way to do this. So if you need 2 different types that work a certain way, you just implement the same method a different way for each of them, and then you subtype from a starting type. So for example, with circle and square, they both implement the getArea method differently, right? But the way that a lot of JavaScript users typically do this is through a different mechanism where they actually just straight up check what the type is, and then they just do different stuff based on the type. And this is, it doesn't look like it from here, but this is kind of close to what you end up doing in some functional languages as well. You just effectively check some sort of information that's embedded in the runtime, right? Some sort of tag, or you do some sort of runtime check, and you say in this branch it does this thing, in this branch it does something else, and then we can use some common logic to like tie them all together. But this is a little unsatisfying at this point because if you look at this example, the way that we have to encode this is through any, right? The padding variable here. Here, let me zone in on this. The padding variable has the type any, and that's not satisfying because it means that we're effectively just falling back to JavaScript. We're not getting any sort of checking, and it's dangerous because if we have a property, if we try to access a property that doesn't exist, we'll get undefined, and that'll kind of like ruin our day, right? And so what you effectively want to say is that padding has either the type number or it has some object type with a count and a car property. And so that leads us to union types. And so union types allow you to say that you have a type that is one or the other, right? It's a fixed set of types. And so just as an example of this in action, I'm going to show this just for a minute. We're starting off with some code. And again, it takes a padding parameter of type any. And if we hover over a couple of things here, right? If we hover over padding here, we actually see that the padding variable has the type any. But we also do this type of check to see if the type of padding is number. Within that branch, if I hover over padding, that has the type number. And so we use control flow analysis and these things called type guards. We actually recognize certain specific constructs in JavaScript to know this is a pretty well-known pattern of checking whether or not something has the type. We can use control flow analysis to say that within this branch of the function, it has the type number, even though it has the type any from the top. But in the absence of that, right, all we can determine in the other branch is that you have any's, and that's not good. So we can actually write out it's either number or options. And now, if I hover over padding in the else branch, I see that padding has the type options. And what do you know? I've actually gotten a spelling error. I probably meant char instead of character. This is also handy because it means that if I don't say this is just number or options, I can say it's number or string or options. And now within that else branch, we actually see that we're getting an error because we haven't appropriately handled the case where something is potentially a string. We don't actually know if the count and the car properties are there. And so this is maybe the start of where we feel like we're really getting to to model code that JavaScript users are already writing, right? And this is not like necessarily a novel concept, right? Again, types in programming languages mentions union types, but only in like maybe 2 sentences because it assumes that you're building a language from the ground up with the static type system in mind. So why would you have just union types? You'd only have discriminated union types. And so it's interesting that the underlying runtime lets us just express this with no overhead. But then we start asking ourselves, what other sort of well-known patterns can we express in JavaScript, right? And so this is another really common example.
Wait, did you ask yourself that, or did you notice that people were using this?
We were. I think we really just noticed if people were using these things. Yeah. So I mean,
I can imagine some stuff that TypeScript doesn't have.
Sure. We should talk about future suggestions afterwards. Definitely. Yeah. Okay. In all honesty, like we're not constantly saying like, oh, this was cool. Like, what else could we do? We're really trying to say users came to us with some sort of use case in mind. How can we solve that better, right? But here's a great case where there's a very common pattern in JavaScript code where you just use stringly typed code effectively, right? You say this function takes either the string left or right or center or something like that, right? And so all you can say in most type systems is that that parameter has the type string. You can't do much else with it, or you can't constrain it much more than that. And so what we said was, well, union types allow you to model a well-known set of types. This function expects a well-known set of values. The only difference between those 2 statements is values and types. And so if you actually start to try to think about these things as not distinct ideas, then you can go pretty far. And so we said, what if the strings left and right and center themselves could be literal types, these singleton types, right? So each of these things has a type. And that means that when you actually call this function with a misspelling of center or what the author intended for center to be spelled as, you can get a little red squiggly in your editor, and that's nice. And we can even go further than that, right? Once you actually have union types and once you have union types and you have singleton types, what if you can combine that with control flow analysis to do other things? Like, what if you want to do, you want to define 2 shapes, like circle, which has a radius, and then a square, which which has a side length. It's not shouting at us. So square has a side length, and we want to define a getArea function, which takes either a circle or a square. And so if we try to access the radius property on shapes before we determine anything else about it, it says, well, you don't know if you necessarily have a square. So what we typically do is we add a kind field in JavaScript to try to determine the shapes of the things that we're dealing with. And so if we're dealing with a circle, we'll usually say that we have a kind where the brand is a circle, and otherwise we say that we have a kind that's a square, right? And so now we can actually take a look at the shape's kind field, and we see that it has the type with string literals circle or string literal square. You can say if the kind is equal to circle or square, and I immediately get completion for these two strings. If I misspell circle, I'll get an error. But if I get the right completion here, it's OK with that. And within this branch, I can say shape.radius now, because it's able to use the control flow analysis with the fact that this union type has a bunch of objects with a common field on it. So I can say return math.pi. Oh, gosh. So I'm able to combine these features in a really beautiful way. Was discriminated unions. You can introduce unions of object types where they all have a common field, but you can actually do runtime checks to see the values of them and dispatch accordingly. And so we also start asking, well, we have string literal types. OK, well, could we also have number literal types as well? Like, could 1 be a type and could 0 be a type? And yeah, we said, sure, why can't you have number literal types? And what if true was a type and false was a type? And Booleans were just a union of true and false. What if we can fix nullability in TypeScript? So when we started out with TypeScript, we make this mistake, which is that all types are nullable. And we're not the only ones that make this mistake, right? Like, if you've ever had a null pointer exception in Java or something similar in C# or whatever, Tony Hoare called this the billion-dollar mistake, right? And in JavaScript, you have null and undefined. And so we made a $2 billion mistake, if the math checks out. And so what we... Right. Yeah, so null and undefined are not our best friends, but only because we started out implicitly saying that a number is potentially null or undefined, right? If you think about types as domains, then really it makes no sense that undefined and null is in all of these effectively. And so with union types, we were able to say, what if we can create a new strictness checking mode where instead of each of these things implicitly falling within every other type's domain, they had their own domains, right? Where the undefined value had the type undefined, and the null value had the type null as well. And whenever you want to be able to say that something is potentially undefined, you just use a union type between these two things. So you say it's number or undefined. And the funny thing is, internally in the compiler, we had the null and undefined types, and it just took having the right underlying concepts to enable us to do this. So once you had union types, we could express this in a reasonable way. And so in TypeScript 2.0, we introduced strict null checks. And nowadays, you don't have to write a function and wonder whether or not someone potentially passed you undefined or null. You make that explicit, and otherwise the call site will get an error, right? So non-nullable types, that's one of the bigger things. And at this point, we have done a pretty, what I think is a reasonable job of modeling a lot of common code that exists in the wild, right? We're able to model a lot of common JavaScript patterns. What we're not doing as much of is working with, we have a question?
So you said that 0 is a type then? And 1 is a type. So you earlier said that when you do type inference, you assume that whatever the programmer wrote at the initialization site is accurate, and you're just going to trust that. What if I initialize something to 0? Then you have a special case, or what? Because otherwise you would infer the type is 0.
I implemented string literal type, so this is a fun question for me. So the question is, we take what you wrote at the initialization site as, as the thing that we infer from, right? And so we assume that if you initialize with 0, that's a number. But 0 is itself a type, so why don't we initialize with the type 0? And the reason that we don't, is because that is a pretty useless type on its own, right? Like if we just said you initialize with the string hello, and that's a mutable variable, like what would you ever assign that to afterwards, right? Probably there's nothing that you would want to do with that. And so what we have is two concepts. We have contextual typing and mutability widening. And so if something is going to get assigned to certain mutable locations, we will widen the type to its base primitive type. So for example, you have the string hello. In fact, the string hello actually starts out with the type hello. I'm not lying to you. It actually starts out with the type hello. But then what happens is it walks up the syntactic context to actually see what you're going to be doing with that string. And so, for example, if you're assigning it to a mutable variable, we assume, hey, you probably don't want just the string hello. We'll do mutability widening, and we'll widen that out to string. We also have something called contextual typing. And so if you've actually given an explicit type annotation of the strings hello or world, then we'll see that you actually are going to intend to assign this to something with a literal type. We should keep the literalness of that type around and not widen it at all. So there's the short answer is it's a lot of hacks and heuristics. I shouldn't call it a hack, but type systems have constraints, and that's really what it comes down to. This is the best way to do it without looking through non-local locations to figure out what you're eventually going to do with the value. It took us a while to get there as well, but yeah. I have a question?
Isn't this just an abstract interpretation past where the lattice is just the lattice of type and union is just like literal union?
Yes. So the question. Yeah, the question is this just a system of lattices? And yes, actually, we have a lattice of types, and unions are, we actually have a type called never, which is the bottom type, and that is the empty union. And then we have a type at the top called unknown, which you can think of as the infinite union of types, effectively. And so when you narrow from unknown, you're basically cutting off branches from the rest of the lattice each time. And there's technically two lattices in this type system. There's the union type lattice and there's the object type lattice. Yeah, it's fun. But that's the way that you can look at it as well. So bigger, and to go on this, bigger unions with more members are actually less derived. They're farther up at the top. Whereas object types with more members are more derived. They're closer to the bottom of their lattices. So that's sort of this fun sort of, it's a little bit counterintuitive, effectively, but it's fun stuff to think about.
I guess one way to make it less hacky is that you actually perform widening only when at the use side, not at the definition side, right?
Could we do widening at the use side versus the definition? I think that we had that in mind for a bit, but then, we've played around with something like that where I can't answer that right now, but it's something to consider as well.
I mean, in some sense, you can think of assigning to a mutable variable as a mutable location as a use, right? So that string, hello, starts out with the type hello, but then as soon as the assignment occurs, which just happens to be right away, the variable, the left-hand side that is mutable, is widened because the widening operator says mutable goes to a primitive type. Is that reasonable to think of that?
That's exactly it. Thank you. So the answer to why can't you just use the use sites is effectively, like, what do you consider a use site, right? Because if you're going to assign it to an intermediate variable, then that would widen it, and then you wouldn't get the results you necessarily want. And so this is actually a pain point for a lot of TypeScript users nowadays, even now, because knowing when something will widen or hasn't widened can be slightly frustrating if you use a very immutable style. If you use a very immutable style, then you probably want to keep the literalness constantly because you're not going to reassign it any time in the future. But JavaScript is a mutable language, right? We're not working with standard ML, unfortunately, right? We're stuck with the sorts of things that people write on an everyday basis. To move on, so at this point, we're able to model a lot of things that you might write in everyday JavaScript code, but we're not modeling things that you might be using if you're writing some advanced code, some stuff that does some meta programming and whatnot. And so, around TypeScript 2.1, we're speaking with framework authors. We're speaking with, we're just seeing the way that libraries are being described to TypeScript, and the way that people are expressing their patterns to the type system. And just for some context here, in JavaScript, property accesses are equivalent to element accesses with string literals, right? The idea is objects in JavaScript are a lot like dictionaries. And so fetching the property bar is equivalent to fetching the property with a string named bar. And a lot of frameworks take advantage of things like this. So as an example, Ember is one of the frameworks that we were looking at around this time. And what they do is they have these getter and setter functions, right? And what they do with these things is they actually model a reactivity pattern within the framework. And the get method actually, subscribes, I think, and then the set one just notifies anyone who's subscribed to this one property. But we wanted to be able to model this in a reasonable way. And so I'm going to dive into an example of how we were able to do that. So in this example, we have the parameter obj and prop name. And what you really want to be able to do is say that for obj, I only want to permit potential properties that obj contains. Within that, once I actually have one of those properties, I want to be able to fetch out that property's type for get. So that's actually two different things. So what we can do here is we can say that obj is some sort of t, and we need to be able to say that we need to be able to express the properties of t. So what we did is we introduced this person, let's define this person keys type. We introduced this new operator called keyOf. And what this does is it gives you a union type of string literals of the properties within a given type. So now I have name and age and location as person keys. So we want to be able to say that this get function only accepts keys of t. Well, that's one thing, right? So let's say I get, declare p. If I give it name, that's OK. However, if I say name and I misspell that, it says that name is not assignable to any of the property names of person, right? So we're able to restrict the properties that get is able to take. But we still need to be able to fetch out the values. If I hover over x, right now it's saying that it is a string or a number. And the reason for that is if I take a look at this type for get here, it's saying that it's t of key of t, which is t fetching out the keys of t specifically. So what it's doing is that's called an indexed access type. That literally takes some type and fetches out the properties of the given type. So if I write, for example, person of name, that gives me a string. I say person of age, gives me a number. And so these two type operators are able to correctly model this get operation. So I can now say that we also have a k type parameter, which is one of the keys of t. And we take a k. And if we look here, it sees that the result is T indexed in with K. And so at this use site, I hover over this and I see the instantiation of person and the string name here, and that gives me a string. And if I index in with the string age, I get a number as well. And so this is really neat because now we can actually model one of the more popular frameworks through our type system, right? This is incredibly powerful. And it's not just Ember, it helps out frameworks like Vue and whatnot. But the idea is we're really trying to get TypeScript to be a type system that can be used with any library, any framework. It needs to be accessible to the entire JavaScript ecosystem. And another concept that we come up with is, at the same time, is used in big part to model another library called React. It wasn't really just React, but it ended up being one of the big use cases. So as an example here, I have this component. A component has some state. And in the library React, we end up having this setState method. setState takes some subset of the fields in the original type that it contains and uses that to update the original type's fields. So what people will typically write is comp.setState. If you have a component of person, it should allow you to specify either name or age or location or some combination thereof. So I can say name, Daniel, and then location, university district, right? But we're just using any, and that's not satisfying. What you kind of want to do is you want to say something like, I have person, but each of the properties is optional. So now I have a name which is optional, and an age which is optional, and location which is optional. And so I can say that this takes a partial person, right? And so then if you misspell location, or if you give it the wrong type, then you'll get an error. And that's good, but it doesn't generalize, right? In this specific context, we have a component for person because we defined the actual types in that context. What we want to be able to do is do something like this for any type. And so if you kind of break this problem down, the only difference between partial person and person is that we've uniformly made properties optional. So what we did is we came up with a new concept called mapped object types. And we can now create a helper type that takes another type and maps over each property. So we'll say for each key, k in key of t, I want to fetch out the original type. And so this will create an optionalized person. If we hover over this, this is identical, right? It is basically copied over each of the properties from the original type person and, recreated its, and just fetched out its type, right? But now we can also say that optionalize marks each of the members as optional. So now a partial person is something that takes each property and marks the property as undefined and copies the original type. We can do other things with this construct, like mark them all as read-only. So now it marks each of the properties as read-only as well. We can say that it's the array version of the original type as well. So we can say it's an array of t of k. And now we're left with string arrays or undefined for each of these properties. And so this uniform mapping is extremely useful because now we can say, we take an optionalized t, right? And so now we appropriately get the right error, saying that number is not assignable to string. What's going on here?
You didn't put question mark.
Ouch. Okay. No, but this is super handy because now we can express. Now, not only can you just cut down on boilerplate, right? You can also express these other patterns. So that's sort of our type system in a nutshell. I mean, these are sort of the highlights, I think. There's plenty more if we dove in. We've got a gradual structural generic type system. We do inference where we can, but we allow escape hatches. We don't try to necessarily stay to like just OO code, which is like a perception problem that we dealt with for a long time. We also try to we try to model functional patterns as well. We have type constructors that are extremely expressive. We have a question?
Why don't we have arrow type?
Arrow types?
Yeah.
Arrow types are, so why don't we have arrow types? Arrow types, I think you mean like function types. Yeah. Function types are a specific type of object types, actually. Let me really quickly dive in here because I want to just show you how the type system works. You can say type foo is equal to x of type number to string. This is a function from numbers to strings. But the thing is that in JavaScript, functions are actually objects. And so the equivalent to this is something with what we call a call signature. So object types, in addition to properties, can have call signatures. And we say that it takes a number and returns a string. And this is useful because now you can say, you also have a property called foo on the function as well. But it's not necessarily a type of, it's not a type constructor per se. It's a thing that is on object types. Yeah. It's sort of the way you have to do this to model JavaScript. And we have these novel type constructors that can iterate through properties, and you can fetch properties out. And some people ask, like, at what point does your type system just become like Turing complete? And actually, the examples that I just showed you are the point where it became Turing complete. So our type system is Turing complete, but we, it typically, it's not a problem per se until you get to the out-of-memory problems that we deal with occasionally as well. But because of that, we said, we'd also add conditional types. So you can actually make decisions within your type system based on the types that you're given in your program. And so there's a lot of expressivity you get with that as well. So a big part of our job is also to take these higher level type constructors and make sense of them. So we're actually doing some level of type algebra in the type system as well. So we're saying, we're simplifying types to say that T or never is just T because never is just the 0 element type. Intersections with never, again, that's kind of like, multiplication with 0 effectively. And then we correctly measure variances, and we simplify type operators over unions and things like that. And so, what I really kind of love about this is it really does model the way that a lot of JavaScript users write their code. It matches the intuition, and it's not just a type system that was it's about restricting the sorts of things that you can do. Because you're already given JavaScript, we have to strive to give you the expressivity, or else we would have failed miserably, right? And so that's why I showed you this code at the beginning, which is, I'll start to say it again, retrofitting a type system into a language not designed for type checking in mind can be tricky. Ideally, language design should go hand in hand with type system design. And so the question I have for all of you is this necessarily correct? Is this true? Should language design go hand in hand with type system design? I think some of you might see this presentation and say yes. Some of you might say no. My opinion is it's somewhere in between. So thank you very much. And I guess we can move into QA if we have that. Okay.